Welcome to this school. Thanks to the organizers. It's, I think for many of us, especially for me, it's the first opportunity to talk in front of a live audience in like 2 years or something like that. So what I will talk about, so the title of my 2 lectures that I will present here is, let's see, what was the title? Cryptographic applications of graph pebbling. So I hear I don't know, it's very, okay, much better. No, because I hear myself very loud. So, okay. So it's called Cryptographic Application of Graph Pebbling, and I will cover 3 applications of this. So what happened with this topic, so obviously graph pebbling, as you will see, is a combinatorial technique. But in all these applications that I will tell you about, so these are applications I worked on, and in none of these applications a priori we thought that pebbling would be useful. In all 3 cases, what happened is we tried to work on that problem, we tried to make progress, and in all 3 cases, independently, pebbling techniques popped up and turned out to be exactly the right tool to understand and to make progress on these topics. So the topic I will cover today, and most of the time actually, is going to be about memory hard functions, because I cannot cover all 3 areas in full breadth, and we will see how far we get. I'm not even sure if I will finish today with the memory hard functions, and then on Wednesday, I have the second lecture where I will much more shortly and only on the whiteboard cover proofs of space and adaptive security reductions in cryptography. Okay, so if you have questions, please just raise your hand. It's important. I hope I'm not going to go too fast. I tend to speak too fast and go too fast, so please, stop me and ask. Thanks. Ask if there anything you would like to know. So the presentation will be like a little bit hybrid. I will do stuff on the whiteboard, but much, for time reasons, actually much of the whiteboard I actually already prepared for you, so you can see it there. So what is graph pebbling? In a nutshell, it's a game, maybe a full information game if you want. It's a game played on a directed acyclic graph. So a directed acyclic graph is given by a set of nodes and a set of directed edges, and it's acyclic, which means there is no cycles in that graph. And for the sake of this talk today, and actually also on Wednesday, we will only look at DAGs which have, let's see, I have a pointer here, right? Like DAGs like here, which have exactly one source. So a source is a vertex within degree 0, and exactly one sink. So a sink is a vertex without degree 0. And the goal of the game is basically to put a pebble, so pebble are little stones, right, so that you can shift around. The goal of the game is to put a pebble on the sink, on this one. That's it. And, there are many different rules and variants of this game, and we will look at 3 of them. We will look at sequential and parallel black pebbling games, and then we will also look at, not today, we will just look at the sequential and parallel, and on Wednesday, when we talk about adaptive security notions, we will also look at a notion that is called reversible. So what are the rules of this very simple game? Here are the rules. The game is round-based, so it's also not really a game between 2 persons. It's really just a game with 1 person. So I played that game with myself, like solitaire or something. I have like this bunch of pebbles here, and I have to put this pebble on the sink, and the rule is as following. In each round, it's round-based, I can put a pebble on a vertex, but only if and only if all the parents of that vertex are pebbled, right? So what does that mean? Just for clarity, right? So if you have like if it looks like this, for example, this is like a subgraph. When can I put a pebble on this node? I can only put the pebble on this node if and only if its 2 parents are pebbled. So in this case, I can put one there, right? And otherwise not. This is the parallel the sequential rules. In the parallel black pebbling game, the only difference is that I can put as many pebbles as I want in each round. But each pebble has to satisfy this condition that I can only put a pebble if all the parents are pebbled. And then once I put all the pebbles I want, I can actually remove all the pebbles I want. So I can take pebbles off the board. And here, with taking pebbles off the board, there is a difference between the normal pebbling, black pebbling, and the reversible black pebbling, because in the reversible black pebbling, I'm not allowed just to take off any pebbles. I'm only allowed to remove a pebble if I would also be allowed to put a pebble on that node. So I'm only allowed to take a pebble away, right? So this would be okay. I'm only allowed to put a pebble away in the reversible black pebbling game if all the parents are pebbled. So this would, for example, if it looks like this, I don't know. This would not be okay in the reversible black pebbling game, but it is okay in the normal, non-reversible. If we don't say reversible explicitly, it means non-reversible. So in the normal black pebbling game, you can remove whatever you want. In the reversible ones, you're only allowed to remove a pebble if all the parents are pebbled. You know, so far, this is just a game. Actually, these pebbling games are by no means new. They actually originated, I think, in theoretical computer science somewhere already in the 70s, originally for proving reductions and lower bounds, like simulating multi-tape Turing machines on single-tape Turing machines. More recently, pebbling is used in proof complexity proofs, to bound the complexity of resolution proofs, things like that. So pebbling has many applications. And today I hopefully will convince you that they also have very cool applications in cryptography. Okay, any questions to this game? Because it's we will go through it a few more times as we see examples and things like that, but it's very important that the rules are clear. And as the rules are clear, okay. So now that we defined the game, yes? I mean, you will never need more than there are nodes on the graph if you look at finite graphs. So I think that, if I give you a bag of pebbles to play with, I will never have to give you a bag bigger than the graph. But we will now look at the complexity that we will discuss now. Yes? What? Yeah, so when does the game start? The game starts typically, there are many differences. Sometimes when you discuss our proof of space later, we actually will start with pre-pebbles. Some pebbles are already there. But in the game for now, we start with the empty graph. And the goal is to end with the graph which has exactly one pebble on the sink and nothing else. As you already see, the nothing else doesn't matter for the normal black pebbling game because you can just in the last round remove everything except that. But for the reversible, it's actually a thing because you have to get rid of everything else. So it makes this condition will make the game more difficult. Okay, so a little bit of notation. So, our base object that we will often see is just this directed acyclic graph. We use standard notation, right? So I hope you know this. So a graph is given by a set of vertices, like just a set of, or nodes sometimes called, and a set of directed edges E. And then there is a dedicated thing, which we call capital T, simply because the notation is taken from the paper where capital T is actually the set of target nodes that you have to pebble, but for this talk, the target set is always just going to be a sink, so we don't need the more general case. Now, we have the notion of a pebbling configuration. So what is a pebbling configuration? It's simply a subset of the nodes. It's simply a subset of the nodes, and we think of a pebbling configuration as the nodes on which a pebble is lying. And then you have the notion of a legal sequence of a legal pebbling sequence. So what is this? This is simply a sequence of pebblings that could have come up in this game that I defined you before. So we have the first pebbling configuration, P0, which is implicitly it's always the empty set. Then we have the final one, which is called here PT, which is always going to be the sink. That's the one node the sink is in that set. And then we have some configurations in between, and they have to follow some rules, of course. And the rules are, this is written here in this, in the standard notation. So for any pebbling configuration Pi, it has to be the case that if some vertex X is in Pi, but not in Pi minus 1, so it has been put on the vertex in this, on the graph in this particular round, then all the parents of X, so the parents, to recap, parent of a node is a node that has a directed edge towards that node, right? I think this parent and sibling, I think this notion comes, I think, originally from, because graphs and trees were used in evolutionary biology, so they had this descendant trees, right? So the parents are up and they point down to the kids, and the kids have siblings and childs that are the outgoing ones, and ancestors is everything that can be reached from a node. So I hope this notion is more or less familiar. Yes? It's hard to hear you because the ventilation is so loud. Please speak. What? Zoom in, yes, of course. Let's see. Okay, then I will just slowly. Yeah, maybe I should have started and turned it. Yes?
I have a question about the parallel notion.
Yeah?
So the rule is after the one parallel step, all the rules are satisfied. It's not that each individual step in that parallel step has to fulfill.
No, each individual. So, I mean, otherwise you could do it sequentially. So you have one round, and you can say, I want to put the pebble here, here, and here. And for each individual pebble, it has to be true that, in the sequential game, you could also have put it. For each game.
If you, for example, take the first example, you could put one node to the right
No, so this would, I don't know what it means. You mean this. Sorry. You start with something like that, and you say, oh, I put the pebble here, and then I can immediately put one here.
Yeah, exactly.
No,
so
this would no, because, no, you have to, you look at the graph, and you give me a set of,
okay.
This is exactly this. I mean, that's exactly why we actually also look formally at it here. It exactly says, you can only have a, what does it say? Let's parse it, right? You can, for every node X that pops up in configuration Pi but was not in Pi minus 1, it is the case that in the configuration before Pi minus 1, all the parents were already pebbled.
Okay, so parallel step is just multiple sequential steps.
Exactly.
In one.
It's still more powerful than sequential because I can put many things, but of course, otherwise it wouldn't make sense. Otherwise I could pebble the entire graph in one round, no matter what it is, right? You can always just topologically put everything in. Okay. And again, we sometimes say that something is a legal sequential pebbling sequence or something is a legal parallel pebbling sequence, and the only difference is that in a sequential pebbling sequence, the number of new pebbles in each round can be at most 1, whereas in a parallel one, you can have as many as you want, as long as each one individually satisfies those rules. Okay. And then still a little bit more notation. Having defined like a valid pebbling sequence, we can also define the set of legal pebblings of a particular graph G. So this is this calligraphic P subscript G. With this, I will simply define the set of all possible sequences of sets corresponding to pebbling configurations that are valid pebblings of that graph. And whenever I have the superscript, this one, like this parallel thing, this always means, I mean the parallel version, right? So this is just for notation. And of course, the sequential pebblings is a subset of the parallel ones, right? Obviously. This is, and for all interesting graphs, of course, a proper subset. Okay. Now that we talk about, we have defined what pebblings are, not all pebblings are made equal. Of course, we will be interested in pebblings having particular complexities. And, there are actually several things you can ask for. And different problems that you want to model as pebbling problems will kind of ask for different complexity notions that you try to optimize. So here are like 4 notions of complexities that I want to define that we will use today. Namely, time complexity, space complexity, time-space complexity, and cumulative complexity. So for a given pebbling sequence, like here, we define the time complexity simply as the number of steps it needed. So if the sequence needed 57 steps to put a pebble on the sink, the time complexity is t. The space complexity of a pebbling sequence is the maximum number of pebbles in any of the sequences. So if I needed like 1 pebble, then 2 pebbles, then 3, and then so on, but there was one configuration with 125 pebbles, that's going to be my complexity, space complexity. The space-time complexity is simply the product of the previous 2. So if it's the product. So what does this capture? As we will see later, we use these pebbling configurations, so these pebbling configurations to model computations. And what will typically happen is this rule that you can only put the pebble on a node if the parents are pebbled corresponds to the fact that you can only compute the value corresponding to that node if the previous values are actually somehow known and stored. So this ST complexity basically corresponds to the case where you have like one instance of a problem, and you know that you will need T steps to compute it, and S tells you how much memory you will need. So this ST complexity gives you, if you want, the size of a circuit, for example, that you would need to kind of evaluate that particular function. And then another thing that will be very important is the cumulative complexity, cumulative memory complexity sometimes, which is simply, here is the cumulative pebbling complexity, which is simply the sum of the numbers of pebbles in all configurations, right? I have a nice picture here to illustrate this. So you see this, this skyline here. So the x-axis are just like t different pebbling, it's a pebbling sequence of length t. The height of this skyline that you see is the number of pebbles that are in each of those pebbling configurations. Then, if you look at this picture, this space times complexity will simply be the surface of this square, right? It's the t, the time complexity, times the space complexity, which is the maximum number of pebbles in any configurations, which is this. So this green thing is going to be our space-time complexity, and the cumulative complexity is kind of this red thing. It's simply the surface under the skyline. Okay. And having defined these things, now having defined complexities of particular pebbling sequences, I can now start talking about, yes? I'd really help with the mic because it's loud.
Can you hear me now?
Yeah.
Perfect. Could you give some intuition about the space-time complexity? Like the way I would have naturally defined it would have been the number of consecutive steps that need the maximum amount of space.
What's the question?
So, like, can you give some intuition about the definition of the space-time complexity? Like the way I would have naturally defined it.
When I will talk about applications, we will see exactly, sometimes ST will be the right complexity measure, sometimes CC will be the right complexity measure. So if you want ST complexity, just to say, if you have like a, not a single instance of a problem, you can't batch problems. You get like some input and you want to compute it. And then this, you ask yourself, what is, what kind of hardware how do I need to kind of compute these things? Then basically the ST complexity will somehow give you the cost of evaluating this function, because it says you need that much space, which is the S complexity, for that much time, which is the T complexity. And the fact that, sometimes you need less or more, it's not going to help you because you cannot accumulate, it's just going to be empty. Whereas CC complexity is going to be more important if we talk about, batched computation. We can accumulate stuff, then really just the stuff under the skyline is important, because if you have less, you can actually make progress on a different instance or things like that. We will see that in a second.
Thank you.
Okay, but now so that we have defined the complexities of particular sequences of so Pebbling sequences, we can now start defining the complexity of a graph, and this is ultimately what we will care about. So for alpha, let alpha be any of those notions that we had: space-times, or cumulative, and then we can say that there is Don't point it at me. So? Is this on? No? Okay, I don't know. It's very psychedelic. Okay, let's try it. So for alpha being any of those, you can, in your head stick, let alpha be any of those four notions that we've discussed so far: space-time, or cumulative. And then we can talk about the alpha Pebbling complexity of a graph as follows. So we will use this notion as you see here, this capital pi. The subscript is going to define the notion, and this G is going to be the graph. So the complexity of these graphs for this notion alpha is simply the minimum over all possible valid Pebbling sequences for that particular notion, right? And again, if we have this superscript here, this parallel lines, it means we take the minimum over all parallel Pebbling sequences, and this is then called, the parallel complexity of that graph, parallel space complexity or time complexity, whatever you want. And okay, let's see. Don't look for a second. Oh, come on. I can drive, right? Okay. He lets me draw, but he doesn't let me delete. Okay, too bad. I was thinking that I want to prepare those slides and actually first make them, then delete some stuff so I can fill it in during the talk. But apparently, I didn't delete, which is maybe good because I can't delete now anyways. Okay. So what are some simple inequalities from these notions? I mean, of course, parallel is always like the set of parallel pebblings is a superset of the sequential pebbling. So of course, this means it can only make the complexity low, because you can always, whenever you can do something sequential, you can do exactly the same pebbling parallel, but not vice versa. So the pebbling complexity, say for space-time, or the pebbling complexity for cumulative pebbling is always going to be less than the sequential counterpart. Moreover, space-time complexity is always larger than the cumulative complexity, because if you have the skyline, the surface under the skyline is always less than the box encircling the skyline. So here are just, I hope this inequality should be really clear to you now, if you understood if you're still following the definitions. Okay, so let's look at a few very simple examples. Let's take the complete graph. So what is the complete graph? The complete DAG is simply defined as a graph where you have nodes 1, 2, 3, 4, and so on. And node I has incoming edges from every node from 1 to I minus 1. Right? So it's a complete graph, but it's directed, and it has to be acyclic. So this way, if node I has incoming edges from everything from 1 to I minus 1, it's clear that this is an acyclic graph. And another simple example is the path, which will be the node of Qn. So Qn is simply the path, like a graph that is basically just a line, right? The node 1, 2, 3, and you only have edges from node I to I plus 1. And let's see. What do we know about, let's see. What do we know, for example, about the space-time complexity of the complete graph? So how many steps do you need at least? I mean, you can only pebble node I if node I minus 1 has been pebbled. So obviously you will need n steps. And how many pebbles do you need on the graph? I mean, if you look at the very last step, it has ingoing edges from node 1 to n minus 1. So all of those have to be pebbled to put the pebble on node n. So it's going to be something like n times n minus 1 at least, right? So it's n squared, more or less. It's going to be the ST complexity. So this is shown here, right? So the ST complexity is basically n times n minus 1. As said, this is, what about the cumulative complexity? Yeah, it's not much better. It's kind of a factor 2 less, simply because you start with putting a node, pebble on node 1, then on 2 and 3 and 4, and you will never remove pebbles, because to pebble node I, you need everything that was there before. It's kind of quite obvious that this is the best strategy. So in fact, for the, this is important to remember. For the complete graph, the space-time complexity and the cumulative complexity are kind of very close. The cumulative, and even if I would let you, even if I would put a parallel here, actually, right? It wouldn't help. Okay. What about the path? Yeah, the path is actually quite easy to pebble. We don't have magnets, and magnets would be good. How would you pebble a path? Right, I guess in the first step, you put the pebble here. In the second step, you put the pebble here, and you remove that pebble. In the third step, you put the pebble here, but you remove the previous one, and so on. So actually, the complexity is just n. Right? No matter if cumulative or space-time, you never need more than one pebble at any configuration. Again, very simple examples. And in this talk today, we will actually look at interesting graphs, beyond these kind of things. But before I will talk more about interesting graphs and pebbling configurations and how to construct graphs with that have various complexities and so on, let's look at an application that motivates the first application that actually I'm aware of that I worked on where this notion came up. And these were memory hard functions. So what's a memory hard functions and how is it used? So one of the main applications of memory hard functions is something called password authentication. I don't know what you think. So if you have this Wi-Fi, this Wi-Fi password here, you make a password and so on, and then you set it up, and then there is some database somewhere, and this database has your login, which here I think is your email address, your login, and some password. Right? So let's say this is the server here. And how do you think this is organized? Naively, so I think if you for the first time making such a system, you would probably have a server. This server would have this nice database with logins and passwords, of course, somehow sorted, so you can efficiently check if a login is actually in your database. And then if Alice here wants to log into the server, she will say, look, I'm Alice, here's my password. The server checks, yeah, indeed, Alice, I have that login, and indeed the password she sent me is the password that I have stored. Here, Alice, you have your Wi-Fi access, or whatever is there. So why is this not how it's done today? A major problem or a major attack vector that such password servers have is that this database is, of course, extremely valuable target. Depending, of course, for what it is, but assuming that this is some interesting access credentials, you want to protect it. And servers get hacked all the time. This database is just if you look in the news, there's like 100 million passwords stolen here, 20 billion passwords stolen there, and things like that, right? So if an adversary here, so Black Hat here, gets the database, he can just impersonate whoever he wants, period. Nothing you can do. So people have thought, how can we improve the situation a little bit? And one idea, I think it's from the 60s already, was to say, okay, listen, don't store the password in the clear. Actually, the server does not have to store, instead of storing the password, just store a hash of the password, right? So very simple. So here, if you see instead of 1, 2, 3, 4, the password, I store the hash. And I call the hash function f here. Now, if Alice wants to authenticate, she still sends, her login and her password. And what the server will check now, he will take the password, hash it, and check if the hash matches what he has locally stored. Why is this good? Let's go back to the setting where we have Black Hat. He steals the database, but now he's in a much worse position, right? Because he doesn't have the logins and the passwords. He has the logins and the hashes of the passwords. But if he wants to authenticate to the server, he now first has to figure out the preimage of that hash. Like if the hash is SHA-256, preimage pretty much means he has to actually find the password that Alice used. Otherwise, he would even found a collision, and this is presumably very hard. Okay, so are we done? This is good enough. You know, if you look at passwords that people choose and actually can memorize, they don't have terribly much entropy. So the uncertainty, entropy is a measure for uncertainty of passwords. Typical password, even with all these constraints that tells you, one capital letter, one small letter, one special character, it's hardly more than 30 bits or something of entropy. And 30 bits means that it's something like 2 to the 30 attempts you will actually be able to find a preimage of a password. So people added a few more extra, tricks to make the game for the black hat even harder. One that I just mentioned because it's good to know about, has nothing to do with what we're talking today, is one is salting. So instead of having Alice and her password and locally storing the login and the hash of the password, the server for every password additionally samples locally a high entropy string, or sufficiently high, like a string that almost certainly will not have repetitions. And then he will not hash the password, but the hash word and the salt, how it's called. Okay, otherwise the game is exactly the same. If Alice logs in, he kind of takes the password, he looks up Alice in his database, he takes the salt that he stored together with that login, hashes the password and the salt, and checks if it matches what he has locally stored. How does this make the life for the adversary harder? I mean, it makes it harder because now at least the adversary has to attack each password individually. Before, in this case, right? Sorry if it looks like this. Maybe the hash function f is maybe hmac of SHA-256, something like that. The adversary could just kind of prepare a list, a gigantic list of a few terabytes with hashes of the 1 billion most popular passwords, and then basically just for each entry in that database, just look it up if he has had it stored. In the new setting with the salting, it makes his life at least a little bit harder. At least he has now to start attacking one particular password and start kind of brute forcing, trying out many different hashes with that particular salt. We're already progressing, we're better. Okay, is this, with salting, are we done? Actually, we're still not done. And I had somewhere this complexity. Okay. Oh, no, okay, this comes later. So are we done? It's still not good enough. Look, as said, even 2 to the 30 computation to break one individual password, totally feasible today, right? No problem. That's kind of the problem with Moore's law, right? As 30 years ago, a 30-bit entropy password might actually have been quite a challenge for the adversary to do, right? But as in the last decades, the computing power went up by, 20 orders of magnitude, but our brain capacity to memorize passwords stayed the same. Now we're in a much worse situation. Now actually you can brute force passwords that people can typically memorize in minutes or seconds and so on. So we can counter this. And people said, okay, instead of using SHA-256 or whatever, some standard off-the-shelf hash function, make this function that you use for hashing the password artificially difficult, artificially hard to compute. So, and this is called like a moderately hard function. So when I say moderately hard function, you should think of a function that the server can evaluate in a few tens of milliseconds, maybe hundreds of milliseconds, right? SHA-256 would be, I don't know, probably microseconds, right? But something that takes the server in some computation, but kind of not so much that he couldn't kind of compute it once for every login attempt that he sees. And one famous one, maybe even the one used now with the Wi-Fi here, which is used in VPA2, was simply it's called password-based key derivation function 2. It's not called password hashing because actually you derive, instead of kind of hashing it and then checking the hash, you actually use that final hash as a key for a session and so on, but the technicalities. But what they said is the following: said, okay, instead of just hashing once, just hash many times sequentially. For example, VPA2, that was probably by now not because it's insecure, that was used for encrypting Wi-Fi connections, uses exactly this very simple function. The hash function itself is SHA-1 in HMAC mode if the input is too long. Then there's a password. The salt is the SSID. I don't actually know what this is. This must be some random value that comes up somewhere in the process as you set it up. I don't know. You repeat it 4,096 times, the function sequentially, and then the last parameter is the length. This is the final output length of the, because as I said, you actually use that key for something else later. Okay, so this is, if you hear password-based key derivation function 2, that's basically a moderately hard function to derive such a, to derive, in this key, a key from the password. Okay. So let's look at the rationale of these moderately hard functions. What is the idea here? The idea is, say, look, the server has to do this computation with this moderately hard function once, I don't know, if he has, how many login attempts he has per hour. It's kind of a quite overseeable number, typically. On the other hand, Black Hat, so the guy who tries to brute force your database, he will, for each password, he will have to try billions and billions or trillions of possible passwords. So actually, if I make the computation hard, it kind of is slightly annoying for the server, but for Black Hat, it hopefully makes it kind of totally infeasible to brute force anything. But this is intuition true. It's important that, so once this, these moderately hard functions were introduced, it became clear that, the adversary doesn't have to play by the rules. The server is the server is what it is. It is a server. It has some kind of general purpose CPUs, and on that general purpose CPU, it has to compute the hash function that he has to evaluate and so on. But the adversary who wants to brute force these gigantic databases of passwords, he can use very dedicated hardware that does nothing else than compute, say, SHA-256. For example, so in particular, these things are called ASICs, application-specific integrated circuits. This typically refers to kind of circuits that are not general-purpose CPUs, but kind of very particular circuitry that is customized to kind of make compute one particular function very good. I mean, these things became popular with, Bitcoin and things like that, because like all this mining hardware these days is ASICs, right? People used to mine Bitcoin on their laptops, but today this is no longer feasible. So why is this a problem? The problem is that if you use an ASIC instead of a general purpose CPU, the cost of evaluating a hash, and what is the cost? The cost is the energy cost, like how much energy do you actually need for each of such computation. It's also the hardware cost. If I have like $1, how many the hardware I get for that, how many hashes per second does it perform? So these are basically the two major cost factors, and both of them are kind of, by a factor in the ballpark of 1 million or so apart between ASICs and general purpose CPUs. So the server, even though we make this moderately hard function to make the life for the server hard, we actually manage, but the problem is, the adversary actually starts with a factor 1 million head start anyways. So that's kind of unfortunate. So then people thought, okay, can we fix this problem? So, and then there was this field of this term that came up, which was called egalitarian function. So egalitarian here means, it's not like a socialist term, but it rather meant people wanted functions where you cannot get much of cost saving by computing the function of general purpose hardware as opposed to kind of on a normal off-the-shelf server. And how can you compute such a, how can you construct such an egalitarian function? So there were several ideas, but the one that really kind of won, I think, it's the only kind of really reasonable approach today, is to use memory hard functions. So this was proposed originally by Percival in 2009. And he said the following: look, the hardware for the adversary is just much cheaper than for the general purpose servers. But if you want to compute a function, you typically not only need the hardware, like the cores, but you also need some memory. And memory costs too. And he said, let's make a function where the cost, even on the server, is not dominated by the server, by the CPU, but the cost is dominated by the memory cost. So if I want to compute this function, I need like, a gigabyte of memory for 1 million steps, something like that. So then, okay, you still have a CPU that makes the hashing and so on, but the actual cost is the memory. And there is no such thing as application-specific memory. So if you have memory, you can use it on the server for a general purpose task. There is no kind of, at least we don't know of it, there is no special memory that you could use just for kind of computing a particular function or things like that. So it just has to store random strings. You maybe can use memory of lower quality, or that has a few bugs or something maybe, but basically, if you had a function where the cost is dominated by the memory, hopefully you would get like a really nice egalitarian function where things are not so bad. And what is the concrete function that Percival proposed? So the function that Percival proposed is called scrypt, secure. I forgot what the acronym stands for. And it's a very simple function. Let me draw it on this blackboard, maybe. So even though it's also on this one, he said, you take the initial. So the function itself is based on a compression function. So you need some building block, and the building block is simply going to be a hash function h, maybe SHA-256 in h mode, that takes strings of length 2W at least. Think of W as a statistical security parameter, 128 bits, 256 bits, something like that. It maps it to, to half of it. Okay, so this is the building block. And the function itself is very simple. So he has this input, let's call the input x. You first hash it somehow, maybe with HMAC mode if the input is very long, to a first value, and we call this the label 1. Label 0, sorry. So as you see, I'm actually mapping a computation to a graph, and you can kind of see where this is going in the end, right? So at some point we will close the cycle, and then we will talk about pebblings. So once you computed the hash of the password, you just continue doing it. Actually exactly like in PB, password-based key derivation hash function 2, you just compute it for n steps. So so far that's actually no progress over PB, K, DF, H2. But then, once you did this first n steps, now we start to do something interesting. Now, after n steps, you make n more hashes. But now, the next step, so let me use a different function. So this is going to be maybe black. What happens now is, to compute the next label, ln plus 1, you not only take as input the previous label, so you want the function to be kind of sequential, so you compute this label sequentially. You not only take the previous one, but you also compute, I think actually, sorry, this should be n minus 1 for reasons. So you also compute, you take this value, ln minus 1, you compute it modulo n. So basically, this is basically a random value because it was computed by a function that behaves sufficiently randomly. You take it modulo n, which gives you a random value between 0 and n minus 1. So you think of it as picking a random value that you have already computed. Let's call this I. And then you dynamically add another, this is Li. You add another edge to your graph. And so to compute this next value, you not only need the previous label, but also a label, the label Li, where the index of the label I depends on the value on the label that you've just computed before. And then you do the same trick, the same computation up to L2n minus 1 for n more steps. So what is the kind of the intuition here? Why should this be a memory hot function? Why should this be a function that needs a lot of memory to compute? So if you had to implement this, how would you implement this as a program? You probably would compute the first n minus 1 values, store them, and then as you progress, you would also kind of just access the position that you kind of need to access to get it. Okay. Yes?
Thanks. So in the example graphs that we'll be seeing related to computational models, will it always be the case that the straight line graph will be a subgraph of the graph? Like,
if you want to have graphs that are somewhat hard, it's kind of a good idea to just start with the path and then add vertices. It's not a requirement, and in fact there exist some hard to pebble graphs that don't have this structure, but it's not a requirement, but it's a good thing to do. If you have a path underlying the graph, you immediately, for example, know that the time complexity is at least t. Because, there is the time complexity for pebbling a graph is at least the length of the longest path in that graph, right? So it's a good, so no, it's not necessary to have a path, but it's kind of, all the graphs that are used in this context you start with the path and then you start thinking, what else should I add? Basically, that's it.
Thanks. Another small question. So this memory hardness, is it somehow inspired by this thing, this bounded storage model or something where you...
Not really, no. I mean, there is a relation simply by the fact that both of them talk about somehow. So here you need a lot of memory to compute the function. In the bounded storage model, you have actually a very large key that, or some kind of value that is kind of distributed, or so bounded storage actually you would a very large key that then you assume an adversary cannot retrieve in full, and because of that, if you just have a partial, like a compressed key, it's useless for him. But pebbling techniques have also been used actually in the bounded storage model, right? I think Stefan Jambowski, Daniel Wicks have this paper about I forgot. So it's a bounded storage model where a function progresses forward, and because if the memory storage is somehow bounded, you can never go back. And this is really kind of basically Pebbling pyramids graph. So this is also kind of one of the paper where Pebbling comes up, but that I will not talk about. But it's actually, I guess, it's for people not working on these areas. It's confusing. The memory hard functions, proof of space, bounded storage, and all these things. Everything talks about some kind of space being limited in one way or another. But for different flavors. So it's related, but different.
Thank you.
Yeah.
So I'm a bit confused why this function is memory hard at the moment. So let's say I keep L0. That is my first one.
Yeah.
Then to compute till Ln, I can just keep L0 and like forget everything that I compute at each step, right?
Yes, that you can do.
And then I have Ln and L0. So I can get Ln plus 1. Then I hash L0 and get L1, then remove L0, and then I have L1 and Ln plus 1, and then I can get the next one. So each time I'm only keeping 3 things in memory.
Yes, we will discuss this. Indeed, so you can actually compute this function. Scrypt is not how we would call, there's another notion like sustained space complexity. You can actually compute it with very little memory, but actually at very long time, you need a lot of time. Basically, we will later look at it. If you look at the CC complexity, for example, like how much storage, the analog of the Pebbling CC Pebbling complexity with actual memory, it's true you can do it with much less memory, but then you need it for much longer. It's actually, I will discuss this, and it's a good point. It's actually a problem.
It's 2n and n the difference, right?
What?
So, because then if I want to do it like with more memory, I can just compute the n first and then do everything else like parallelly somehow. But it's just twice the time.
No, you see, the point is you only learn this, you also see this, you only learn this edge once you computed the previous value. Actually, this is a good, I actually wanted to discuss this. It makes a huge difference if you compute Scrypt like this, where you only learn this edge here once you computed the previous value, versus like you could think it as a kind of a static variant of Scrypt, where once you computed ln, maybe you compute you learn all the edges at once.
Oh, okay.
That would kill you. That would be terrible. Yeah.
Okay, thank you.
It's, actually, at the end of the day, I don't want to talk about Scrypt because I will talk about different graphs. So, before we can talk about, what is is it this memory hard function? What does that even mean? We need like a computational model because so far we just talked about, putting pebbles on graphs. That's not a computational model. That's not how computers work. They don't put pebbles on graphs or anything. But the computational model we look at is called the random oracle model or the parallel random oracle model. So to make unconditional statements at the end about the space required for a particular function to be evaluated and so on, that's hard, right? In complexity, we cannot even prove P does not equal NP. We cannot prove anything unconditionally hard. So we will, to be able to prove things unconditionally, we will work in this, this dream world, which is called the random oracle model. I mean, who here has not heard of the random oracle model? Okay, so exactly. So I hope all of you have heard this. Basically, this is a model that cryptographers like a lot. They say, okay, look, my protocol, whatever thing, uses some hash function. I want to prove something, but for the sake of the proof, I will assume that my hash function behaves like a perfectly random function. So somehow I think of there being some kind of oracle in the sky that has like an exponential size, uniformly randomly sampled function table, and every time everyone can make queries to that function in the sky. And if I make a query X, this oracle looks up in this exponential size list entry X and gives you the corresponding value. Right, so this is the random oracle model. And so that's the model we work on. So concretely, we have this, now it's called A. So A is adversary, but think of it as basically the party that wants to perform some computation. This party gets some initial input X, and then the computation proceeds in rounds. In each round, A can come up with a list of queries they want to make to the oracle. Right? So we call them like Q11, Q21, Q, and so on. Okay. And once it made this list, this list is sent to the oracle, and what he gets back are the corresponding query answers. He gets the output of the random oracle on his queries. And then A can write something, it's called sigma 1, to its memory. It has also memory. It can say my new memory state is going to be called sigma 1. Okay, fine. Then it gets the memory. Okay, that was the end of the first round. In the second round, A has access to its memory. It can, if it wants, it can read out the entire memory sigma 1. then it can come, it's computationally unbounded. The only thing that we limit is the number of queries that A can make. So A can come up with a new list of queries that he wants to make to the oracle. He sends it to the oracle. He gets back like a list of outputs, HQ2, up to, and so on. And this game moves on, right? Sorry, it's a bit cut off. So is this game clear? What is important in each round, A first retrieves the memory it has, this sigma I, this memory state at, after round I, makes any computation, and then can update the memory to the next state, sigma I plus 1. Right? Okay, I hope this is, so this is the parallel random oracle model. The normal random oracle model is the same, except that in each round, the adversary can only make one query to the random oracle. Okay. So having defined such a computational model, and we can now talk about the complexity, about the cost of something of such a computation. And we defined before the cumulative Pebbling complexity, and now we define something quite similar, which is called the cumulative memory complexity of A. And this is simply this here. So remember, the cumulative Pebbling complexity was the number of pebbles in each step, and the cumulative memory complexity is simply the sum of the size of the memory, whatever data is in there, in each step. So it's again this this skyline that you see, and the cumulative memory complexity is the surface, this black surface under this thing, right? So it's basically the. And then, analogous to the space-time Pebbling complexity, we also have like a space-time memory complexity, if you want. And this is simply the number of steps multiplied with the amount of data that was in the memory at the time point where it was highest. So there was some sigma I that is bigger than anything else. Right here, in this case, it would be the step 2. Then the ST complexity is simply going to be, this box. So this is the complex. So ST complexity is not the right term. Actually, typically people talk about something area time complexity in terms of circuits, and then it's more complicated because this is the memory and also has some surface for the computational part. So I kind of dumped it down a little bit for the sake of this talk because these other things are just important if you actually want to analyze things. But for the theoretical results I want to show you today, these are kind of the two clean models that you somehow, I hope, mentally have now in your head. Right, so you have this model, I do a computation, I make the random oracle queries, I have a memory where I write state back. I do this computation, and then somebody looks at the transcript and says, okay, your memory, your cumulative memory complexity was this, your space-time complexity was this, your time complexity was the number of rounds, and so on, right? So you have all these complexities that you can talk about now for that particular execution of a computation. And okay, now that we defined the, the complexity of a particular execution of a particular algorithm on a particular input, we can talk about the complexity of a particular function. Exactly as before we talked about the Pebbling complexity of a graph, now we can talk about the complexity of a function. So in particular, the cumulative memory complexity of a function f, how should I define it? I define it simply as the cumulative memory complexity of the best algorithm computing this function. Yeah, so here. Now, again, this is a bit oversimplified. I probably should take the expected complexity over a random choice of x and so on, but I kind of just swipe over these things for now, just kind of to have a simple mental model. If you have a function, the cumulative memory complexity of that function is basically the cumulative memory complexity that any algorithm needs to kind of compute this particular function on, let's say, worst case input, if you want. Okay. Now, which complexities should, okay, let's go back to our password hashing game. So which complexities should we use, for example, for the honest server or for Black Hat and so on? So let's recap. The Black Hat, the bad guy, first of all, he has many, many cores. He has this ASICs, and he can kind of, parallelize it pretty much as he wants. He can buy 100 cores and make like 100 queries. So, and the function itself that we, the building, the compression function itself that we use is kind of built as a random oracle, but Black Hat kind of lives in the parallel random oracle model because he has many things, so we can make many questions in parallel. Moreover, we should probably talk about the cumulative memory complexity for him, not the space-time complexity, because he will kind of attack a lot of passwords at the same time. So even if the memory he needs during the computation varies widely, he can kind of amortize it to make sure that most of his memory is kind of well filled most of the time. So really the surface under the skyline is what is important. So if we talk about the complexity of Black Hat, the adversary, we will talk about the cumulative memory complexity, which we will, at the end, which we want to be high, right? So this notion is very nice, parallel, cumulative, but we want it to be high. On the other hand, for the server, yeah, he will has a, 10 years ago I would have said 1 core. Today I probably have to say at most 16 or something like that. But let's say he just has 1 core. So we want to model this server just as a normal random oracle computation. You can only make 1 query to the random oracle in each round. And moreover, he gets those queries in one after the other, more or less. So let's use space-time complexity to be on the safe side, right? So we really charge the server the maximum memory that he needs during the entire computation of that particular hash function. Because probably what he will do is he will block that memory for the entire duration of the computation and just compute it. So that's kind of basically the cost that we have to charge for. Now, let's go back to our script example to see what the complexities are there. And let me already tell you, we will not prove anything about script because this is would be beyond this talk. But I will just state you the results, and then we actually go and construct stuff. Let's see. How can I want to peek what is next without giving it away. Okay. So what do people think? Let's say the server. How would the server compute this function? How would it compute it? So this is the space. This would be the time. So the space, or memory, let's call this the memory. The server would probably first compute the L first labels and just store everything. Why not, right? So this, let's call this here. This would be roughly W times n bits. That's how it's going to look like. So it's a step function, but right? It computes this. And then, and then it just computes like one label after the other and goes on. So the space-time complexity would be this here. So we get space-time complexity approximately what? 2n times n times w. So it's something like, So this w is basically the length of the label, this 256 bits. But basically, the complexity is n squared. You need n in the order of n steps. In each step, typically, you have to store in the order of n labels, so roughly n squared times w, right? Now the question is, what is the cumulative memory complexity? I mean, this is this question has been open for quite some time. People kind of, it was conjectured basically implicitly in Parseval that it's also in the same ballpark. It's also going to be something like some constant times n squared times w. But good luck proving this. But indeed, it's true. Just let me mention this. So this was actually even the best paper at Eurocrypt 2016 really showed that the cumulative memory complexity for script is indeed n squared times w. There is a little bit of stuff here. It's not w, it's w minus something small, something logarithmic in n. I hope this will become clear. This will become clear later as I show you how these proofs actually work. So this is basically a reminiscent of the proof because you somehow have to. In the proof, it's a compression proof for random oracle. You have to kind of remember a few of the, which query did what. So this is this little log n, but ignore it for now. The bottom, because also w can be as big as you want. It can be much, much bigger than log n. Bottom line being the complexity, the CMC complexity of script is indeed n squared times w. So actually, script has been used because of this nice, it's a nice function. For example, in cryptocurrencies, for example, Litecoin was like an early cryptocurrency, which said, oh, look, in Bitcoin, everyone moves to ASICs because people cannot mine anymore on their custom hardware. So let's use script. So it's an egalitarian function, so it's kind of much fairer. But then there still came people still came up with basically, let's call them ASICs, like dedicated hardware that could compute the stuff much cheaper than general purpose hardware. And the reason was the following: what happened was they said, okay, look. Actually, it was mentioned before. One way to compute script is, you store everything. This is L0 to Ln minus 1. You just store everything, and then, as you go on, you just kind of, you just kind of look up the corresponding value. As you go on, you just look up the corresponding value in what you have stored. But what you could do is, let's just store every x value. Right, and so on, and n minus 1. Think of x as 10. So how could you compute it now? So, this was the original computation. as you would do it. So this is this here, up to n steps. You just fill up everything. This is NW. What you would do now is, okay, you could compute the next step. It would give you some index I that you have to compute, but now you probably have not stored it, unless it happens to be, one of those 0 modulo x, this I. But, with at most x steps, x over 2 in average, you can recompute this thing. And then, actually progress to the next step. You get the other, another step. So the way it's going to look like, it's actually going to look like this. You still this be n times w divided by x, right? Actually, what's going to look like, it's going to look like this, sorry, right? So you first store like a x fraction of the actual values. But now you need more steps. You need something like 2, let's see, n. How much do you need more? Plus, let's see, n over x times 2, something like that. Typically, you need x over 2 steps extra for each of those n steps that you need to go on. So it's going to look like this. Now, you see, this doesn't contradict the fact that scrypt is memory hard. Because if you look at this surface, n times x multiplied with nw divided by x, you still get something in the ballpark of n squared times w. But now, you also need more computational steps. You need to kind of evaluate this function x times more often than the simple evaluation. But indeed, the memory you need is much smaller. And what happened with this dedicated hardware that computed scrypt super fast is they chose x so that they actually could store this entire initial values in cache, not in memory. And having stuff in cache means you can access it much, much faster and much cheaper than kind of fetching it every time from memory. So they kind of made this hardware that had everything in cache, and so they could compute it. They could compute this thing super fast. And actually, at the end of the day, if you do the calculation, they were much cheaper than doing the memory stuff. So this is a problem. Actually, something I will not talk about. There are now different notions that kind of capture this. There's something called sustained space complexity, which basically not only requires that this surface here is high, because this is the surface here is the CMC, but actually that there is a very large, that for many of the steps, the memory is very high. Basically here, what you would ideally have is that for a linear, theta n number of steps, a constant fraction of those n steps, needs something in the order of NW memory. scrypt does not have this. We will see graphs, we will see functions today which do. But okay, so this was the, this is basically the state of the art for data-dependent MHFs. So what are data-dependent MHFs? So, okay. So let's have a little bit more discussion here. So what we wanted, right? So I hope what we wanted from this memory hard function, so for this moderately hard function, was that the server has so first of all, you assume that the cost is dominated by the memory. So the cost for the server is basically dominated by this STC cost. That's one thing. Moreover, this cost for the server, right, sequential non-parallel model cost, is within a constant factor of of the parallel random oracle model and the cumulative complexity, which means that the adversary, amortizing many executions, parallelizing things, does not get a much cheaper evaluation than the honest guys, because he has a much better hardware. He has these ASICs, they are cheaper, but the cost is in the memory anyway. So the fact that his computation is cheaper doesn't really buy him much. So these are the two things. So these are the two things that we wanted, and there is yet another thing that we wanted, to be memory. But I will discuss these things here. A long time ago, like an hour ago, we discussed these Pebbling complexities. Actually, here I should have. Instead of Pebbling complexities, here I should have. So instead of using scrypt, for example, why don't we just use, for example, the complete graph? I told you before for the complete graph. I told it for the Pebbling, not for the memory, right? But I told you for the complete graph, space-time complexity and cumulative complexity is basically the same. We will see later today that, Pebbling complexities imply memory complexities, so you can actually equate them in your head if you want already. Why don't we use Kn? Why don't we use the complete graph as a memory, as a moderately hard function? What's the problem? See, it's easily defined, right? It's like this path, and this label here is computed as the hash of all the labels before. Yes? Yeah, so costly, yeah. So, I made some assumption at the beginning, right? I said we start with some building block that we actually can build, like from scratch, like a compression function, say mapping 512 bits to whatever, 256 bits. If you would use a complete graph as a memory hard function, suddenly you have like this 1 gigabyte of data that you have to hash to compute the next label. But it's a circular argument, so how do you hash this gigantic thing? So what you would actually do is you probably, if you, for some reason you wanted to use the complete graph, you would probably use like, some standard Merkle-Domgard hashing, right? You would kind of take the input, break it up into blocks, and so on. This would be the hash function h, and so on, until you compute the final value. Why not? Not very good, because this already needs linear time in the input length. And even worse, now this function here, so this would be the new h that you use. This function here is not kind of memory hard, because what I could do is I could just take this input here, compute this value here, and then delete everything in the past, then delete everything here, then just kind of take this value here, compute this value here on this thing, delete this, and so on. So it's not, it's really important that we start with the building block that is kind of, takes a short input and compresses it a bit, rather than something that is, a priori unbounded, because then you kind of don't really have you don't have a guideline how to construct the memory hard functions, because you have to implement it, and then you have to use a function with large input, and you don't have such an ideal object. Okay. So why not use a path? So actually we discussed the path. Like the password-based key derivation function is a path, and also for the path, actually the space-time complexity and the right, I missed something here. I should say it's really important that here this is also the parallel stuff, right? Also for the path, the sequential space-time complexity, the parallel CC complexity, roughly the same. Great function. Why not use? Oh, and the hash function is even better than in S-script. It's just W to W bits, right? It's just even length preserving. So why not use a path? What was the problem there? I'm just recapping things to see if. What was the problem with the path? So yes? This too, yeah, but S-script has it too, so that aspect is not even worse. Yes? What? With masks?
We didn't need to store all of them.
What?
All of the paths, like in Merkle-Domgard.
No, but what did I say? What was the rationale of memory hard functions? The cost is dominated by memory. Or maybe that's what I said, okay. But for a path, the cost is not really dominated by memory. You don't need memory, right? You just kind of compute it sequentially. And so if you really, S-script is only really good if you kind of take all these things into account. So first of all, you want something, where the memory cost to start with here. You don't even want n times w. So n times w would be, in principle, you just need constant memory for each of the steps or something like that. So you really want something that fills the memory as fast as possible. And in the sequential ROM model, where you can only make one query, the best you can hope for is that, basically the best strategy is to compute those values sequentially and never delete them. And if you do this for n steps, you basically have something like n steps where the memory is of size n times w, ballpark. So the best you can hope for is something like n squared times w, as S-script has. So it fills it up as fast as possible. So you can get memory hardness quite. So it's optimal memory hard in that sense, if you assume that the honest evaluation that the server only has one core. And in all other aspects too, right? This kind of compression function is 2w to w. That's also nice. And the hard thing to prove, even with these two conditions, still the complexity in the cumulative parallel model and the sequential non-parallel model is roughly the same. Okay, that was about S-script. Okay, so these were the questions and these were the answers. Are we done? We have this super nice object. Modulo, this minor thing that I mentioned about, about actually maybe instead of CC, maybe actually wants to stay in space, but like modulo, this minor issue. Are we done? Why are people not using script? In fact, people are using script or functions that are of this type that maybe don't have this little problem for many applications. Like for blockchains, this is the perfect application. So in password hashing, there is kind of one problem. So password hashing is typically done on the server. And servers succumb to things like cache timing, side channel attacks, and this thing. I'm sure many of you have heard about these things. So what one can do is, even if there is somewhere a server, let's say the server runs several tasks, for example, even if I run a totally independent task on that server than, let's say, the password checking thing, it's possible to get some information about what the other thread is doing. And this information is usually the leakage that you can get from the other thread is typically what type of memory, so which cells of memory or blocks of memory, it's to some granularity, the other process does actually access. So these are these cache timing attacks and lots of things, because if the other process, so in the memory is arranged in these rows, if the other process accesses something in that row, and then my process tries to fetch something from that row, it will take longer because it kicked out the stuff in cache, which always takes only values from that particular row, things like that. But not important for the sake of this talk. But what is important is that one of the most easily attainable leakages about like other processes on if you have like a shared resource like a server is actually this memory access patterns. Now, what does this mean if a process evaluates script? So assume there is a process like, that evaluates script on that server, like step by step, and my process somehow gets a hinge about the memory accesses. And look what could happen. So in this particular case, what is extremely important is that once I compute ln, I have to access what? I have to access ln minus 1 modulo I, right? Because I have to access this particular value, which sits somewhere in memory. So let's assume actually somehow this is leakage that the adversary gets. You might not get exactly I, but like kind of a range for it. But let's assume the adversary somehow attains this. And once you get this extra leakage, okay, and there is yet another thing. I told you the adversary wants to brute force passwords. So what this means is for a given hash, he wants to find the preimage. But actually the function that he really wants to brute force is not what is the value of, if I hash this particular password X, what is the output? But what he wants to know is this particular value X, does it match that particular output that I want to find? This is somewhat the easier question. In particular, if I know that this other thread was evaluating actually the correct password X, right? And I got this leakage I, and now I have some candidate input X prime, and I want to know, is this X prime the same as X or not? What could I do? If I have no extra information, I just have to recompute X prime, take X prime as input to script, recompute the output, and check if I get the right value or not. But if I have this extra leakage thing, I can just compute X prime up to this value ln, and just check if I get the same value I. Because n is actually billion. So in almost every case, if I have the wrong X prime, I can immediately dismiss it as not being the same as X, because I see that the first kind of adaptive memory access for X and X prime was actually somewhat different, and I can immediately throw it away. So this little extra information, the first kind of memory access when computing that password, gives me a lot of information that I can use to brute force the password much easier. Because you see, once I have this I only have to compute this initial path here, and this initial path is very cheap. This has CMC n, not n squared, right? Because I just compute this path. So now suddenly with this little bit of extra information about the leakage, the CMC drops from n squared to n. And this is something that people didn't like. So they said, look, I don't know, to me this still looks like a very far-fetched attack, but apparently these memory attacks are super easy these days, and everything comes to it, so they would like to have functions which do not succumb to it. Again, in the context of blockchains for proof of work mining, that's not the problem. Nobody cares about these leakages. We just locally kind of try to kind of find some value that satisfies some constraints. But like for password hashing and so on, that's a thing. So because of that, if you talk about MHFs, people will always talk about two different types of MHFs, namely data-dependent and data-independent. So a data-dependent MHF is a memory hot function where the memory access pattern depends on the actual input X. So script is an archetypical example of a memory of a data-dependent MHF. Because, you know, once I have X, for different inputs, the access pattern will look totally different. A data-independent memory hot function is a function where the data access pattern is totally independent. I mean, the values are, of course, different, but the access pattern to the memory is totally independent of the actual value. So, you know, password-based key derivation function 2 is data-independent. Of course, it's not memory hard, as we discussed before, but it's, at least it's data-independent, right? It's kind of just this pattern. So what we will do, I don't know how far we get. We probably will still finish it up only on Wednesday, but, you know, now we will actually use pebbling strategies and things like that to actually construct data-independent memory hard functions. So what is our goal for, let's say, maybe the next 20 minutes and maybe the first part of the lecture on Wednesday? We want to construct a function that, let's say again, as before, is based on some compression function. And for reasons that we discussed before, we want it to be kind of a simple compression function that takes like some short input and, you know, hashes it even down to something even shorter. And what we want is the other property that we want. We want the cumulative parallel memory complexity to be roughly the same as the space-time complexity in the sequential model for reasons discussed before, because we want the cost for the adversary to be similar to the honest guys. And you remember for S-script, we had like this great thing. We had like, you know, the cost was n squared times W. And then, you know, the ST was the same up to some little constant. Here, we will have to give up a little bit. We will not be as good. We will have this extra log n factor. So the CMC and also the space-time complexity is going to be something like n squared times W divided by log n. And in fact, this is the best possible. Actually, for this particular problem, if the function has fixed input and you want to have n steps, that's the best you can possibly get. Actually, that's the best you can get in the parallel random oracle model for any such function. So we just have to live with the fact that here the space is a little bit worse, but, you know, not much, right? It's still pretty good. Okay, we need a plan. Here's the plan. And actually, we will do the plan backwards. But the plan towards constructing this data-independent memory hot function is the following. First, maybe let me actually define it from the end. So we want to last as step C. So we want to end up with functions that have these particular properties, right? But this is kind of a computational model with random oracles, adversaries that make queries and stuff like that. That's ugly. So the first thing we will show is that if you give me some fixed graph that has some kind of high pebbling cost, space or time, space-time, cumulative, parallel or not, I don't know. If you have such a graph with high pebbling cost, this implies in the random oracle model that you get a function from it that has high complexity, the corresponding one. If you start with cumulative parallel pebbling complexity, you get something with cumulative parallel memory complexity. And the function is going to be very simple, right? The function simply takes the graph and then defines this labeling function. So we will see it in a second. So this is going to be step C, which we will do first in the proof. Okay. So now we have to have, so now we're left with the task of getting graphs with high pebbling complexity. And what we will do is, I will give you a very elegant proof, very simple, that some graphs which have a combinatorial property that is called depth robustness, something introduced in the 70s by Erdős and Graham and Shemeredi. So these graphs are the depth robust, which is like a very clean combinatorial property, implies graphs that have high, these graphs not implies. The same graph also has high pebbling complexity, which is a much more complicated definition, right? We're putting pebbles and games and rounds and so on. Depth robustness is a much cleaner, super nice property that, combinatorists half century ago have already analyzed. And then we're left with kind of constructing a graph with high depth robustness. As said, this has been solved for us in the 70s. I will show you the modern constructions we have. I will not give you the full proof because the proofs are just very, very tedious. But I give you the intuition of the construction and then, okay. So I think what we will do for today is step C. And I guess, I'm not sure if we managed to do B. So let's go step C. Let's recap what is step C. I want to show you that if you give me a graph that has high pebbling complexity, I will give you a graph that has high memory complexity. Or, high complexity in the random oracle model for whatever complexity you care about, space-time, cumulative. So here is you know, here is what we start with. So that's what we assume, and later we'll prove how to get it using dev robust graphs. So we assume, somehow, magically, there exists an infinite family of graphs, this, you know, Gn indexed by natural numbers, graphs of in degree 2. So if I have this notion, this Gn2 means all DAGs on n vertices where the maximum in degree is 2. Okay, no? And this family of DAGs has the following nice property. The space-time complexity in the parallel black Pebbling model, and also the cumulative memory complexity in this, the space-time complexity in the sequential Pebbling model, and also the cumulative complexity in the parallel model are both roughly the same and very high, namely n squared over log n. Right, so this is, that's what we start with. Okay, now, having such a graph, okay, this is, sorry, that is. Having such a graph and some compression function, like a random oracle, let's say, like a random oracle that compresses to W bits, I want to define the function of interest, right? The function that I later want to show is memory hard. And this function is simply defined as the labeling function that we have actually already seen many examples of before. So if we start with this, you know, toy DAG like here, this one, right? It's a DAG on three vertices. I derive from it a function f as follows. Typically, sorry, this L1 should be L0. You will also start with L0. First of all, I take the input x and I hash it, and this is going to be my, this is going to be the label, I call it, the label of the unique source. So I should mention we will only look at DAGs, as I said, 1.5 hours ago now. We will only look at DAGs with a single sink and a single source. So you take the input, you hash it, that's the label of your source. And then you define each other label in this graph as follows. The label of any node, like say the label of L3 here, is simply this function h applied to the labels of its parents. So you can always topologically somehow compute this function, and the output of this function is simply the label of the last, of the sink, right? Clear? We have a graph, we have a compression function, we have a graph of in degree 2, we have such a compression function taking 2W bits, and I map this graph on the function. And now I want to show you that if this graph has some high Pebbling complexity, this function has some high memory complexity. How do we prove this? Let's first look at the trivial direction, the other one. Namely, if the graph is easy to pebble, then the function is easy to compute. So, to make a concrete statement, let's say the space-time complexity, you could also, as said, if you want, you can make it parallel. Instead of space-time, you can also take CC, whatever you want, right? So, but for concreteness, let's say the space-time complexity. If the space-time complexity of the function is upper bounded by the Pebbling space-time complexity of the graph, multiplied by W, which is just the length of the labels, right? For each pebble corresponds to a W-bit label, but basically, if I can, the space-time complexity is whatever, 1 billion, then the Pebbling complexity, then the space-time complexity. Sorry, if the Pebbling, wait, is this W correct? Yeah, that's correct. Okay, so how would one prove this? I mean, proof is a strong word here. So basically what you do is the following. Let's delete stuff. You simply emulate, you simply let the, so we have our function here. And somebody comes and gives us one particular Pebbling strategy. He says, put the pebble here, then put the pebble here. Yeah, this is like really not a good graph, huh? It's like, sorry, let's make it a little bit more interesting. Like this, okay. Put the pebble here, then put the pebble here, then put the pebble here, and then put the pebble here. Right? I hope this is a valid sequential pebbling. I put the pebble here, then in the next step I put one here, I remove this one, then I put one here. Oh, so this is a parallel pebbling. I put one here, and then in the same step I put one here. and then I recompute this, right? So what is the ST complexity? I have 2 pebbles and 1, 2, 3, 4. 2 pebbles, 4 steps, ST complexity is 8. So how can I compute this function using ST memory complexity Fn 8 times W? So what I do is I will simply emulate the pebbling using the random oracle model. Like, so what this adversary does is he takes this as input, this pebbling sequence, and he simply, oh, first I have to compute this label 1. Great, actually remember you take this input X and I get this label 1. And I store label 1. In the second step, so this is the memory, right? In the second step, okay, I retrieve the label 1, and my next query is actually going to be L1. And I get back L2. And I store L2. And so on. And next step, oh, I compute L2 and also X. I get back L1 and L3, and so on. Yeah, you get the idea. And if it's clear that whatever is in the memory corresponds exactly, the number of labels in memory correspond exactly basically to the number of pebbles, and so on. Now you could be pedantic and say, oh, but you need some extra information to understand what these labels mean, and so on. But forget it. It's basically the same. You can hard code he needs a counter to know in which round he is. But this is the trivial direction. The non-trivial direction is the ex post facto pebbling. 10 minutes. Okay, let's actually try to get through it. The ex post facto pebbling. Then we can actually cover more next time. Which basically says the other direction is true too. So for concreteness, I will, here I use for concreteness space-time sequential. Now I will use cumulative memory complexity parallel. So I change notation at some point. At some point I use the P in front of this, but now I would just want to have this. Oh. Let me just use the subscript here. So what I want to prove you is the following. If you have a graph, oh, and I should say something else. For this trivial direction, it actually really doesn't matter what this function h is. This can be a random oracle, this can be SHA-256, this can be bit flips, whatever. This doesn't, we didn't use the security or hardness of h at all. Now, for the other direction, we will crucially rely on the fact that h is a random oracle. Map+ is, uniformly random function. And for concreteness, I will show you this bound. We will look at the cumulative parallel complexity, and I will show you that if you have a bound here, if you have a bound on the cumulative pebbling complexity of GM, then this gives you a bound, basically the same bound on the cumulative memory complexity of Fn, right? So the pebbling complexity basically multiplied with the length of the label, minus something log n small, which is kind of a reminiscent of the reduction, which somehow has to keep track, as you will see, about what value means what and so on, this technicality. So a fundamental lemma that if you do cryptography, theoretical cryptography, special information theoretic cryptography, you will use all the time, is this following simple fact. A random string is incompressible. So if you have a random string, you cannot compress it. The formal statement is shown here. It says the following. Assume you're brilliant. You came up with some encoding, decoding procedure that takes strings of length L and compresses them to length K. And then the decoding procedure takes that compressed string and decodes it to a string of length L. Then this very simple technical lemma says you will fail with decoding in the sense that the probability that the decoded value here is the same as the encoded value is at most 2 to the minus k. So if you don't compress at all, k equals 0, you're fine, right? 2 to the minus k is 1, so you will always compress and decompress correctly because the identity function is a good compressor in this case. But even if you want to compress by just 1 bit, no matter what you do, on a random input, you will always fail with decoding. Of course, we have compression algorithms. You always compress your files and so on. But of course, they exploit the fact that the input is not uniformly random, that you compress, but kind of is very structured, and actually, it has much less entropy than its length. Okay, so here is the first time we use this simple fact in our proof. So the proof techniques that I will use to prove you that this, that pebbling implies memory complexity is called something ex post facto pebbling. The name comes from the fact that ex post facto, that I let the adversary run, then I look at this transcript, and from this transcript I extract the pebbling configuration, and and basically the pebbling configuration has low complexity if the adversary had low complexity in that transcript. And if I know that there exists no pebbling configuration with some low complexity, I know that the transcript could not have had small complexity to start with. That's kind of the high-level idea, but I will hold you by the hand and we will go step by step through this argument. So the first observation is, look, this random oracle is incompressible. Think of W as 256. Like, what I'm pretty sure about this, right? I have this adversary who kind of, let's see. Let's go back to this computational model. I have this adversary. He gets some input X, which is random. He makes these queries. He can't make whatever queries he wants, right? But that somehow, at the end of the day, we want him to output the label of the sink. And along the way, he kind of will compute other labels, probably. And what you can say with almost certainty is the following. If in this computation, the following thing will never happen, almost certainly. It will never happen that the adversary uses a label, one of those labels, as the input to the random oracle before having explicitly received it. Right? This is a freaking 256-bit uniformly random string. The chance that I just ask that string as the input before actually having queried that random oracle and get that particular value, forget it. It will never happen. Right? The sun will burn down before you kind of see such an event happen. So I'm not even going to make this particular point formal, but we just start with this assumption. So whatever the adversary does, he does this computation. He computes the final label. Every label that he uses as input has been received previously as the output on the other query. So in particular, these labels must be somehow being computed by the adversary sequentially. And assume not actually. So if I had to prove it, how would I prove it? I would say, give me such an adversary where this actually happens occasionally. That occasionally he just kind of guesses this label. But then I can compress the random oracle function table, which I cannot because of this. I would simply take that adversary and say, look, I compress it as follows. Instead of giving you the function table of the random oracle, I let that adversary run. I give you all the output inputs as the outputs that you have to provide to him. And I give you a pointer and says, look, at this point, this guy will actually compute that label. So that point, and then you can actually compress the entire function table by this 256 bits. And that pointer that I have to give you to say where this happens, this is basically this minus log n bits that always pops up everywhere. That's the high-level idea how you would formally prove that it never ever happens that such a label pops up magically somewhere. And I hope right. If you look at the proofs, they are always very technical. They always go, assume there is an adversary who with some probability epsilon actually this label pops up, then here is a decompression function that kind of, contradicts this particular fact. We will not go through this step by step. You know what, it's 5 minutes. This is a very nice argument. I actually would like to recap it on Wednesday, I think. Because what? My lectures today? Oh, okay. Okay, then actually even better, then you have it still fresh. Okay, I thought I have more time to prepare the second lecture, but it's okay. Let's leave it for the afternoon, okay?